All right, well, we'll stop hoping and get to the next lecture. Okay, so our last lecture that we have on logic proper now is going over a theory of definition. So, quickly remind ourselves of the basic components of an axiomatic system. We have our axioms, obviously, which give us our starting assumptions that we start to prove from. We have our primitives. Those are the operators, terms, and relations that show up in the axioms. All the symbols that show up in the axioms that aren't symbols of logic are primitives. We have our theorems, which is what we spent the most time on in this course, is what's a theorem, how do we prove a theorem? That's like the majority of logic. And now finally, definitions. We've been using definitions a lot. We've assumed some sort of understanding of definitions a lot. Now let's actually dive into a theory of definitions and how exactly we do these things. And so we're going to start out with Aristotle's version, Aristotle's theory of definition. That's what we're going to start with. Why do we bother with Aristotle's theory of definition and not just jump straight to how exactly we use definition in modern rigorous logic? And the answer is because in 99% of cases, everyone is just using Aristotle's theory. It's good enough. We don't need all of the rigor that we're going to go over today. So I'm going to go over Aristotle's version, and the reason for that is because it's the one you encounter the majority of the time. Because if you're taking some chemistry class or some biology class or whatever, they don't need to be super rigorous. And it's only extremely rigorous courses that need to go beyond what Aristotle lays down. So we'll go over what Aristotle lays down, and then see how it can still get us into trouble, and then how the modern version of a theory of definition evolved off of that. And that's what we'll be covering here. For those of you who did philosophy, this is all going to be stuff that we already talked about in philosophy. We did way more depth in philosophy than we can do here because we're not doing a deep dive into Aristotle's philosophy. So for Aristotle, we define a species by stating its genus and then a differentiating characteristic. Every definition corresponds to a species. You need to put out of your mind how these words were hijacked in modern biology. How genus and species are used in modern biology is not what we mean here. Every definition corresponds to a species. When you define something, you are defining a species. That's what a definition is. And then a genus, it's a relative term. It's relative to the species you're defining. The same way that parent and child are a relative term. Am I a parent or am I a child? Well, I'm a parent of some people. I'm a child of other people. It's a relative term. In the same sense, genus here is going to be a relative term. The genus is relative to the species you're defining. So get the biology notion out of your head if it's there. So before we jump into what exactly these are, let's just give you some Aristotelian definitions. So taking some examples from geometry, if you go pick some geometry textbook, you'd open it and you'd probably, if you looked up equilateral triangle, you get a definition that looks something like this. What is an equilateral triangle? It is a triangle with all its sides equal in length. So we are defining a new species. Aristotle would call equilateral triangle is a species here. The genus is a collection of objects that we're selecting from. So an equilateral triangle, it's a type of triangle. Triangle here is our genus. With all its side lengths, or all its sides equal in length. Here is our differentiating characteristic. So we're looking at all the triangles. We're selecting from those all the ones that have all their sides equal in length. And the sub-collection that we're left with is the species equilateral triangle. So now, with a concrete example there, let's re-go over what Aristotle thinks of as a definition. We define a species, equilateral triangle, by stating its genus, triangle, and differentiating characteristic. What's the differentiating characteristic of equilateral triangles? They have all their sides equal in length. That's the differentiating characteristic. And now we can repeat the process, because if I gave you this definition, and you wanted to be a somewhat difficult student, you might say, but teacher, what's a triangle? And now I got to give you a definition of triangle. And so I say, triangle, now as the species, notice it was a genus here, now I'm defining a species. Triangle, it's a polygon, there's our genus, with 3 vertices and 3 edges. So take the set of all polygons. Now pick out all those ones that have 3 vertices and 3 edges. And what you picked out are all the triangles. So triangle here is a species. Polygon is a genus. The differentiating characteristic is 3 vertices and 3 edges. Right? Now, if you were being a difficult student, what could you ask me?
What is a polygon?
Yeah, what's the definition of a polygon? Then we repeat the process. So now I'm going to define the species polygon. And I've got to state its genus. It's a plane figure. So a plane figure now is a genus. Look at all the plane figures out there. And now we're going to pick those ones that are composed of a finite and closed polygonal chain. Now, that probably sounds a little bit like mumbo jumbo to you guys. What's a polygonal chain? A polygonal chain is just a bunch of segments all connected to each other. So if I take some polygonal chain and it's closed, the result is a polygon. So, what's a polygon? It's a plane figure composed of a finite and closed polygonal chain. So there's an example of a polygon. What's something that's not? That's not a polygon. Because it's not a bunch of segments all connected to each other. Or if it is, it's somehow like an infinite number if you want to think about it that way. And we could continue with this process. And you can go and you can say, okay, but what's a plane figure now?
Like a two-dimensional space or something?
Right, and so we could continue this chain of thought, and I'm not sure how it's going to continue from here. I'm not sure off the top of my head what a definition for plane figure would be. But let's look at another example now, one from Aristotle directly. I'm not going to give you all the definitions this time, but to follow the same train of thought. When we look at man, meaning like a human being, man is a type of great ape. We're a great ape with the ability to reason, or whatever our differentiating characteristic is from other great apes. What's a great ape? Well, it's a type of primate with whatever the differentiating characteristic is. I don't know. What's a primate? Well, it's a type of mammal with some differentiating characteristic, whatever it is. What's a mammal? Well, it's a type of animal with, I don't know, fur, produces milk, whatever the differentiating characteristics of mammals are. What's an animal? Ah, well, it's a living thing. It's a complex living thing with the ability to move around or whatever the properties of a living thing are. And we keep going. Okay, what's a living thing? What's its definition? And for Aristotle, you remember what came next?
Oh, man.
Went back to a substance.
Oh, yeah.
So what's a living thing? It's a type of substance. It's a substance that has the properties that living things have. And then when you get back to substance, now what? You might say, Aristotle, what's the definition of a substance? What does Aristotle say? Bad question. We've now reached our initial categories, our initial genuses, from which we no longer define. It is not a species, it is only a genus. All these other things we could think about as species and genuses depending on how we were creating our definitions. But once you got to substance, you have now reached the genus that is not a species.
Would you consider a substance to be a primitive?
You see how we're going to differ from Aristotle. So when we define things in our systems, we start with primitive symbols and use primitives to construct more complex definitions. And that's going to be the way that we think of our definitions. But that is not the way that the majority of your textbooks would construct the definition. Your chemistry textbook does not start out by saying, look, here are our axioms of chemistry, and we are going to construct all our definitions from these things. Instead, if you looked at something like a exothermal chemical reaction, what is it? It's a chemical reaction that releases heat. If you went and looked up a chemical reaction, well, they probably say it's this type of reaction. If you went and looked up a reaction, then they say, it's just a reaction, quit it. And for the purposes of this class, that's going to be one of these categories that we don't bother defining.
And you wouldn't consider that a primitive in most cases?
No, it's not a primitive. Remember what a primitive for us now is a technical term.
Right.
See, because you could in chemistry come at it completely axiomatically. But if you did come at chemistry that way, you'd have to start with the axioms of quantum mechanics.
So it's like starting from the bottom versus starting from the top.
It's kind of a way to think about it. I sometimes debate using that analogy.
Sure.
Primitives, starting from the bottom, the most simplest things, and making more and more complex things. Whereas that's not the way most people do it. They start with these categories that we're not going to bother defining, and then start talking about subsets of those categories. And so if you're in a biology class and you got all the way to a living thing, what's the definition of a living thing? They probably say, the things we're talking about in this class are living things. That's what I mean by living thing. And we're not going to try and define that anymore, because that's our top category for the purposes of this class. And so the majority of the time, that's how definitions go. There's these top categories, and from there on out, we're not going to bother defining, and then we create subsets of them as we go. And that's the way the majority of definitions go in the majority of textbooks, and it works the majority of the time. And we don't really need to care about that top category. It's beyond the scope of what we care about in the course. But it's not very rigorous. So, using Aristotle's notion, we ultimately get back to categories as our starting point of definition. Once you have your initial categories, you can start defining from there. But that's not the way we do it in our modern way. We start with primitives and our symbols of logic. And using those, we start to construct our definition. So here's our starting point of definition as opposed to Aristotle's. Categories versus the symbols that show up in our axioms and logical symbols. That's going to be the big difference. So glad you made that connection. Hopefully that connects with your intuition so far. Any questions so far? Okay, so roughly speaking, what were Aristotle's rules for constructing a definition? This kind of gave you the process for how he constructed definitions, but what were the rules that we actually followed in trying to come up with a definition for something? And so for Aristotle, there's 4 rules that you have to follow in constructing a definition. These are the 4 rules of definition. The first one is that a definition must state the essence of a thing. It has to state its essence. If you're going to try and define something, you need to state its essence. It is not enough to state some property that those things have and only those things have. It needs to somehow get an essential property. Now that can be a bit confusing. So there's a good example from antiquity. Prior to Aristotle, there was a definition out there that our definition of man is he's a featherless biped. What's man? It's an animal that walks on 2 legs and doesn't have any feathers. That's what we mean by man. Now it could very well have been the case that when someone uttered this definition, it was true that every being in the universe that was a featherless biped happened to be a man. But this doesn't get at the essence of what it is to be a man. And so the story goes on that someone jokingly plucked a chicken and said, "Behold, man, a featherless biped." Well, no, that's not man. You didn't get at the essence. It's just accidentally the case that all men don't have feathers. So it has to get at the essence of a thing. Number 2, the definition, it may not be circular. Cute little documentary that was pretty famous a few years ago was Matt Walsh did a documentary called What is a Woman? And he went around talking to a bunch of intellectuals and he would ask him, what's a woman? And the most common definition he's given in this documentary is anyone that identifies as a woman. What's a woman? Something that identifies as a woman. Imagine you want to know what foo is. I said foo? That's anything that identifies as a foo. That's what foo is. I've told you absolutely nothing about what foo is. We won't bring up bar. So that is a completely circular definition. It tells you nothing about what a woman is. So it may not be circular. One of the basic rules of definition. Third, it must be stated in the positive. What's an example of a bad definition? What's force? A non-kinematic notion. That's what force is. It's a non-kinematic notion. Not very useful. It doesn't tell me much about force. Okay, it doesn't apply in kinematics, thanks, but what's force?
So defining what it's not isn't
right, stating what it's not, Aristotle says that's not a valid definition. You gotta tell me what it is, not what it isn't. And then finally, it cannot be figurative or obscure. So, I'll give you another one. What is beauty? Beauty is eternity gazing at itself in a mirror. Now you know what beauty is, right? It's eternity gazing at itself in a mirror. Wow, what a definition. So insightful. No, that is completely figurative and obscure. The only thing I learned for beauty is if love is blind, beauty certainly isn't. If it's blind, it can't do any gazing. And there it goes. So, here's a bunch of bad definitions. breaking each of those rules. Now, it might seem at first glance that those are a pretty good set of rules, and if you follow those rules, then you should come up with a good definition. So the question is, why are these rules not enough? And it's not obvious why these rules aren't enough. There's a reason that our theory of definition didn't move past Aristotle for a long time. And here's an example of why these rules are not enough. Let's go back and pretend we're in our system of arithmetic. So you know how to plus, you know how to times, we defined we defined subtraction, we defined division. That system of arithmetic, let's pretend we're in that system. And I say, I'm going to define this new operation, circle. That's not times, that's just a circle. Probably should have done star there. X star y. What do I mean by x star y? I'm going to say x star y equals z, and I'm going to define that to mean x is less than z and y is less than z. That's what it means. X star y equals z means x is less than z and y is less than z. Now, this follows all these rules just fine. Does it get the essence of it? Well, it's not a physical thing, so its essence is just what it is. Is this in any way circular? No. The star symbol shows up over here. It doesn't show up anywhere over there. It's stated in the positive, tells you exactly what it is, and there's nothing figurative about that. You could evaluate this in each case. Is it true? Yes or no? So the question is, what's wrong with a definition like this?
It seems to violate the equality equal symbol in some cases. And I don't know. It's confusing.
So let's plug in some numbers. Let's see. Is it true that 1 star 2 equals 3? Is this true? We're wondering. Well, let's see. What does it mean for 1 star 2 to equal 3? It means 1 is less than 3 and 2 is less than 3. So since 1 is less than 3 and 2 is less than 3, then 1 star 2 equals 3. With me? Similarly, notice that 1 star 2 equals 4. Because 1 is less than 4 and 2 is less than 4, so 1 star 2 equals 4. And now, doing what you were probably thinking, I can combine these two facts. Since this is equal to that and this is equal to that, I get that. Those two things together give me that 3 is equal to 4, which is a contradiction. 3 is definitely not equal to 4. How do I know 3 is not equal to 4? Well, if 3 is equal to 4, we could eventually get 0 equals 1 by just subtracting 1 from each side 3 times. And we know that 0 is not equal to 1 in arithmetic. It's one of our basic axioms. So, this definition enabled us to prove something that should be impossible, namely that 0 was equal to 1. Very bad. Some terminology, just so I don't forget. The definiendum is the thing that possesses the new symbol. The definiens are the things we're using to define the new symbol. So, talk a little bit just about this notation for a second right here. Here I use standard notation for defining something. So we're defining star, and I'm defining it to be logically equivalent to this thing, and you'll notice I put that colon there. The colon there means I'm defining a new symbol, so on this side should be the new symbol. Or in other words, we put the colon on the side with the definiendum. And the definiens are what's on the other side. So common notation, when you're writing out a definition, that definition, definiendum, definiens, not sure if I'll say that, but in case I do, that's what we're talking about. Okay, so any questions so far? And you see why these rules, we can come up with clever situations where those rules just aren't sufficient. We need more structured rules than this.
So you're saying it's a bad definition, this example, is simply because...
We don't want you to be able to insert a definition that enables you to prove something that we shouldn't have been able to prove before.
Because it violates one of the, I forgot what they're called. Axioms, I guess?
Well, it's not that it violates any axioms. It's that we just don't want our definitions to be able to behave this way. It's not what we're after when we're talking about definition. So the next thing we're going to talk about is our two criteria that we want definitions to follow. And so whatever our rules are, we want them to follow, we want them to have these two properties. So we don't want to be able to do stuff like this. I don't want to be able to add a definition to arithmetic and be able to prove something that I couldn't prove before. That would be bad. So we have our two criteria for what we want our definition, how we want our definitions to behave. These are the guiding criteria that determine what our rules of definition are going to be. So these are the criteria, and then we'll get into the rules for how you define each type of symbol. And it has its own rules, although they're all very similar. So here's the two properties we want all our definitions to have. First off, we have the criterion of eliminability. What that means is, in practice, every definition, we should potentially be able to eliminate it. We should never actually need a definition. Definitions are just conveniences. They're just shorthands for talking about a bunch of primitive symbols in one go, or for talking about primitive symbols in a certain arrangement. We should always and forever be able to get rid of the definition and just go back to our primitive symbols. Just go back to exactly what our axioms gave us. So you never actually need a definition. You should always be able to eliminate a definition and still be just fine. All definitions should be eliminatable or eliminable. Okay, so a formula S. So S is what is going to be introducing our definition. So a formula S introducing a new symbol of the system satisfies the criterion of eliminability if and only if, whenever S1, some different formula, so whenever S1 is a formula in which the new symbol occurs, then there exists some other formula S2, such that S1 is logically equivalent to S2, where S2 does not contain the new symbol. So anytime I can come up with a formula that has a new symbol, I better be able to come up with a logically equivalent formula that does not contain that symbol. That's what it means for the symbol to be eliminatable. I can get rid of it somehow. So let's go over a concrete example and then read that definition again. I think it'll make sense. So here's going to be S, some formula introducing a new symbol. This is exactly how we define subtraction when we were doing arithmetic. Let's just remind ourselves, in arithmetic, what were our primitive symbols? In arithmetic, our primitive symbols were plus, times, less than, 0, and 1, right? Those were our primitive symbols. Now, we used addition to define subtraction. So I said x minus y equals z, introducing a new symbol, the minus sign, and we define that to mean x is equal to y plus z. That's what it means for x minus y equals z. X is equal to y plus z. Now, S1 here is now a formula using our new symbol. 13 minus 5 equals 8. Plugging in that definition, that means 13 is equal to 5 plus 8. So notice, S1 and S2 are logically equivalent. They say the exact same thing. S1 has the new symbol, S2 does not have the symbol. S is our formula defining the new symbol. So let's read this criterion one more time and hopefully it makes sense. A formula S, introducing a new symbol of the system, satisfies the criterion of eliminability if and only if, whenever S1 is a formula in which the new symbol occurs, there exists some other formula out there, S2, such that S1 is logically equivalent to S2, where S2 does not contain the new symbol. Or in other words, we should always be able to prove that S1 is logically equivalent to S2. I should be able to show with our new definition that this implies this and this implies this. That's what it means for them to be logically equivalent. So if you're wondering, how do I know that they're logically equivalent? Can you take this, using this definition, prove this? Yeah, just plug it in. Can you take this, using this definition, prove this? Yeah, just plug it in. And now, you might quibble and say, wait a second, I see a 13, I see a 5, I see an 8. Those aren't primitive symbols.
Definitions.
But they are terms that we defined before. So we already defined what 5 and 8 and 13 were. And just to remind you of that, we start out by defining 2. What was the definition of 2? 1 plus 1. And then we can define 3.
1 plus
2 plus 1. And then we can define 4, 3 plus 1, etc. And all the way to 13 is 12 plus 1. So, we were assuming that we had already defined those numbers. We defined those numbers before we defined subtraction. So, our definition here, it used some already defined terms. Our only new term that we were introducing was subtraction when we defined it. Good so far? Not losing you? Okay. Our second criterion that we want our definitions to follow. S is going to be a stand-in for the formula that introduces our new term, like this. So a formula S satisfies the criterion of non-creativity. It satisfies that thing if and only if there is no formula, T, in which the new symbol does not occur, such that S implies T is derivable, but T alone is not. Okay, that sounds like a mouthful. Let's make sense of this for a second. So fancy P here, what's fancy P? This is going to mean all the statements we can assume to be true so far. So this is a conjunction of all my axioms, all the definitions we've gotten so far, and all the theorems we've proven so far. It's everything we know to be true in our system and them all together. So P implies T means that from all the stuff that we have in our system so far, we can prove T. So if fancy P implies T is impossible, but now when I add S together with it, my new definition together with everything we had, T is possible, that is bad. That means that S was in some sense constructive. It enabled me to prove something that we couldn't prove before. So T is some statement in which the new symbol does not occur. So T in no way depends upon S. It's some statement which the symbol does not occur. If it was provable, if T was provable, we shouldn't need S to prove it. It should have been provable just from all our axioms, previous definitions, previous terms. If it was provable. Since the symbol doesn't show up in it. If adding S somehow enables me to prove T, then S is somehow a constructive definition. We want all our definitions to be we say creative here. S is in some sense a creative definition because it creates new things. It enables us to prove things that we couldn't before. We don't want our definitions to do that. Our concrete example of this is exactly what we did over here. Our concrete example is, just erase this. Here's our S right here. Our fancy P, what's our fancy P? Our fancy P is axiom 1 and axiom 2 and ... ending together all the axioms and definitions and theorems that we've proven up to this point. And then what is T? T is a statement 3 equals 4. Sorry. T is a statement 3 equals 4. T is a statement 3 equals 4. In arithmetic, without this definition, I cannot prove 3 equals 4. With this definition, I am now able to prove 3 equals 4. So this definition does not meet the criterion of non-creativity. It enables me to prove some new formula, T, in which the symbol does not occur, that does not use the star symbol, that I couldn't prove before I had the definition. So read this one more time and hopefully it makes sense. A formula S, here's S, satisfies the criterion of non-creativity if and only if there is no formula T. This is going to be one that doesn't satisfy it, so there is going to be a formula T. So a formula S satisfies this criterion if and only if there is no formula T in which the new symbol does not occur. Notice this formula T, the new symbol does not occur. Such that S implies T is derivable, but T alone is not. So once you give me S, I can prove T, but I couldn't prove T by itself without S. So it satisfies this criterion. If there is no statement T out there I can find like this. This one does not satisfy this criterion because I could find a statement T. If we go back to our definition of subtraction, here's one that satisfies this criterion. You cannot use this definition now to prove something like 3 equals 4. This definition in no way helps me prove things that I couldn't prove before. Prove things that don't have the symbol minus in it.
Oh, I see.
Pick any formula that only had symbols that were already defined. If you couldn't prove it before you had subtraction, you should not be able to prove it now that you have subtraction, if it doesn't have the subtraction symbol in it. It's one of those things that you say it 10 times and it clicks, and then you're like, why do you keep repeating yourself?
Yeah, no, this is interesting.
Okay, so these are our criteria that we want for creating our proper definitions. Okay, so what are our rules of proper definition? Depends on what we're defining. Now there's 3 types of things that we can define inside some axiomatic system. We can define what? All our primitives are always what? What are the only symbols that can show up here? So in arithmetic we got plus. What kind of symbol is that? It's a primitive. What kind of primitive is it? What's the difference between plus and 0 here?
Oh, it's an operator?
It's an operator. So we see operators show up. So operators are one of the things we can define. What else do we have there?
So 3 operators and then...
No, 2 operators.
Oh, and...
Less than is a...
Predicate?
A relation or a predicate. Same thing.
Oh, yeah.
A predicate is a relation is a predicate that takes 2 terms.
Yeah.
So we have operators, we have predicates, and then we have...
Terms?
Terms, but these are special types of terms. They're even more nailed down than just terms.
Terms?
They are constants.
Yeah.
So the only things we can define, because whatever shows up as primitives, we're only going to be able to define things like our primitives. Because we're going to be taking certain combinations of primitives together to construct new definitions. So the only things we're going to be able to define are more operators, more predicates, or more constants. And that's it. Those are the only types of things we can define. And those are the only types of things that can show up as our primitive symbols. That make sense? Okay. So, really quick, tell me the difference between an operator and a predicate.
Returns a term versus returning a true or false.
Perfect. Operators take 2 terms and spit out terms. So specifically when we were in arithmetic, plus takes 2 numbers, spits out a number. Times takes 2 numbers, spits out a number. Less than takes 2 numbers and spits out true or false. If I give 1 and 3 to this, it spits out 4. If I give 1 and 3 to this, it spits out 3. If I give 1 and 3 to this, 1's less than 3, it spits out true. Okay. So predicates. An n-term predicate, just a predicate that takes n terms. An n-term predicate, and here's how we're going to list it, P, which takes term x1, x2, x3, xn. It takes n terms. Maybe 2 terms, maybe 1 term, maybe 100 terms. Some n number of terms. So, an n-term predicate, P of x1, x2, xn, we're going to define it to be this symbol s. And it is well defined, I should have said, instead of defined. It is well defined if and only if it has these 3 properties. So these are the 3 properties we must follow in creating a definition of predicates. If you follow these 3 rules, you have now created a well-defined predicate. Rule number 1 is that x1, x2, xn are all distinct variables. What do I mean by that? Let's think about this just in terms of a function. If I were to tell you something like f of x comma y, some function that takes 2 terms, is equal to x squared plus y, and then I give you something like 1 and 2 to plug in there. Plug in 1 for x, we get 1 squared is 1, plus plug in 2 for y, we get 3. So f of 1 and 2 is equal to 3. That is good. Now, imagine that I would have instead said f of x, it takes x, and it's equal to x squared plus x. I repeated my same variable.
That should be fine.
And now, what on earth does f of 1, 2 equal? Well, let's see, we're plugging in 1 for x, so replace all your x's with 1. And we're plugging in 2 for x, so replace all your x's with 2. It's nonsensical. Same thing for predicates. So if I'm defining some predicate in terms of x1, x2, dot, 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 xn, those variables have to be distinct variables. That's what we mean. So row 1, x1, x2, xn are all distinct variables. That's what that's saying. That makes perfect sense what that means?
Yeah, I thought you were defining x and then putting it into both arguments, but I now see what you're saying.
Yeah, no, because when you plug it in, you say replace all your x's with this, and then replace all your x's with this different thing. It doesn't make sense. Whatever goes here is saying what all the x1s should be replaced with. Whatever goes here says what all the x2s should be replaced with. If we had x1s there and x1s there, I could say replace all my x1s with this thing, and replace all my x1s with this other thing. And now, it's broken. Doesn't make sense. So, x1 through xn all have to be distinct variables. Number 2, the formula S has no free variables except the x1, x2, dot, 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 xn. Those are the only free variables that show up in the formula. You can have bound variables, you cannot have free variables. Let me move my camera for a sec, we have that scribble space, and then I'll try and come up with an example to make that appeal to your intuition why. Okay, we can see everything on the board. Can't see that board anymore. Okay, so to give you an example of why bound variables don't break anything, let's imagine that we already have defined for us the loves predicate. So the loves predicate takes x and y, or we could also write it as x loves y. We're assuming that this is defined on all people, and it means exactly what you mean. You can plug in Jack and Jill, it returns true. If you plug in Jack and Vanessa, it returns false. Whatever. With me so far? Okay. Now is that we're going to define a new predicate. And our new predicate we want to define as the is loved predicate. So I want to know this predicate is going to return true if this person is loved, false if they're not. So let's think about the is loved predicate. I'll use I for is loved. It's going to take this person X. What do we mean by this person X is loved? Intuitively, what does it mean that someone's loved?
There's another person.
There exists someone out there who loves them. That's what it means that they're loved. So what do I mean here? I mean that there exists Y, there exists someone out there, Y, such that Y loves X. So now notice, here's our formula S. Maybe right here. Here's our formula S. Following our definition here, this is just P of x1. It's a one-term predicate. And we define it to mean this thing. We're saying that the only free variables that can show up here are the variables here. So there exists someone out there such that that person loves X is what it means that, what I call it, is loved applies to X. Now imagine that I tried saying instead, what does it mean that is loved applies to X? Well, that means that Y loves X. That's what it means. Where's that Y come from? What does that Y reference? So if I make that Y a free variable, now we're back to nonsense. What does that mean? So the only variables that can be free are the ones passed in over here. So that nonsense, but if I scope that with the existential quantifier on the Y, then it made perfect sense to us what we were talking about. There exists a Y out there such that Y loves X is what it means. So S has no free variables except x1, x2, dot, 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 xn, the ones passed in here. Good? Next one. And probably the most obvious one. S only contains logical, primitive, or other defined symbols. All the symbols that show up in a definition have to either be primitives, logical symbols, symbols of our logic, or other defined symbols. So if I go back to making this a good definition, there exists y such that y loves x. I said let's assume that loves was already previously defined. So here's our formula S. L, previously defined symbol. X, Y, Y, there exists, parentheses, parentheses, all symbols of our logic. So all the symbols that show up here are symbols that exist. We're either defined or they're symbols of our logic. If we go back to our definition of subtraction up here, same type of thing. All the symbols over here were either primitives or symbols of logic. Well, except that equals. Where do we get equals?
That is a symbol of logic, isn't it?
That is a symbol of logic. Remember that the logic we are now in is propositional first order predicate logic with identity. So identity is now a symbol of our logic and it doesn't need to be introduced in an axiomatic system. Okay, so some more examples. Defining one that you know and love on arithmetic. The less than or equals operator, and we're going to pass in an x and a y. Now this is strange notation, typically when our predicate, I call it an operator, predicate. Typically when our predicate takes two terms, we write the name in the middle. There's a matter of convention, but this is a perfectly valid way to write less than or equals. Less than or equals applies to x and y. We're going to define that. What does that mean? That means x is less than y, or x is equal to y. Going back to our primitives, here were our primitives for arithmetic. So we use that symbol, and then everything else are just symbols of logic. Perfectly valid definition. Let's define some other predicate, the t predicate. T now takes three terms, x, y, and z. So we can't write it in the middle of them like we could have with this one. What does it mean for t to apply to x, y, and z? Well, it means that x minus y is less than z minus x. Of course, that's what t means. What else could it mean? And let's plug in some numbers to help make sense of these things. So, less than or equals, let's plug in 1 and 3. Remember, this is a predicate, so if I give it two numbers, it better spit out true or false. So less than or equals applies to 1 or 3. Well, let's see. That means replace all my x's with 1s and all my y's with 3s. So I get 1's less than 3 or 1's equal to 3. Is 1 less than 3? 1 less than 3 evaluates to true. 1 equals 3 evaluates to false. True or false evaluates to true. The whole thing evaluates to true. Plug in 1 and 3, it evaluates to true. Let's try plugging in 3, 4, and 1 to this one over here. Replace all our x's with 3s, all our y's with 4s, all our z's with 1s. 3 minus 4 is less than 1 minus 3. What's 3 minus 4? Negative 1. 1 minus 3, negative 2. Is negative 1 less than negative 2? No. So this one evaluates to false.
But it's still a valid definition.
It's still a valid definition. It's just when you pass in 3, 4, and 1, it comes out false. Look, if I would plug 3 and 1 into this, it would come out false.
Yeah.
Plug in 1 and 3, it comes out true. So yeah, it's just a predicate. You plug in numbers, it's going to spit out true or false. And it's a perfectly well-defined predicate. Nothing wrong with it. Just to give you intuition for what this says, it says x is less than the average of y and z. That's what it says. If I'm going to say it, I should probably just show you where that comes from really quick. X is less than y or z. What do? On each side of this, I'm going to add an x and a y. So adding an x and a y to both sides. So I have x here. I'm going to add an x and I'm going to add a y. When I add the y, it's going to cross out with that. When I add an x, my total here is 2x. Over here, I'm going to add an x and a y. The x I added is going to cancel out with that x, and I'm going to be left with z plus y. Now divide both sides by 2. I get x is less than z plus y over 2. Z plus y over 2 is exactly the average of z and y. That's what it means to average two numbers. Take their sum divided by 2. What's the average of 10 and 8? 9. How do you get that? 10 plus 8 is 18 divided by 2, 9. So that's what, okay. Probably not worth the detour. Alright, so there we go, defining predicates. Those are the 3 rules for defining predicates. Pretty straightforward. I think you understand everything there, and the result is still just predicate. Any questions so far before we move on to defining an operation? Okay, defining an operation. Now, an n-term operation, or operator, an operator, these ones happen to just take 2 terms. Not all operators take 2 terms. Some can take more, some can take less. Give you an operator you know and love that just takes one term, the square root operator. If I give it 4, it spits out 2. If I give it 9, it spits out 3. It just takes one number. If I give it 4 and 7, now you're not sure what I'm asking. Okay, so an n-term operator, we'll just use O for generic operator, taking terms x1, x2, xn is equal to w. Remember, it's got to be equal to something because operators take terms and spit out terms. So we're saying when you apply this operator to all these terms, it equals that term. So w here has to be a term if O is going to be an operator. Good so far? So an n-term operator, like O, which takes n terms here, equals w. We define that to be some formula S as its definition, and that is well defined if and only if it has these 3 properties. So let's go over the 3 properties. First off, property 1, exactly what it was down here. x1, x2, xn are all distinct variables. Can't repeat the same variable, otherwise I don't know how to plug in. I don't know what you're saying, it's just nonsense. Number 2, our formula S that we're using to define this operator has no free variables except for x1, x2, xn, and w. Notice that when we said it here, it was just all the free variables were x1, x2, xn. Here, it's all the variables you pass in, and w can also be a free variable when you're defining an operator. In fact, it will be a free variable. And then finally, not finally, 3, S only contains logical, primitive, or defined symbols, identical to this. And then finally, there exists a unique W such that we have S. We have to be able to prove that there exists a unique W such that we have S. So once again, let's go back to our definitions on arithmetic. When we define subtraction on arithmetic, subtraction takes 2 terms. And we said subtraction between x and y equals w, if and only if x is equal to y plus w. Now, you don't like me writing subtraction that way. The way you wanted me to write this is x minus y equals w. Same thing. Subtraction applies to x and w, or x minus y equals w. Same thing. Okay, so how do we define x minus y equals w? We define that to mean x is equal to y plus w. Notice, here's our operator with its 2 terms, and w, and notice that they all show up as free variables over here, which is fine. X can be a free variable, y can be a free variable, and the w can also be a free variable. Oh, I rewrote it right there. Now I have the same thing. Okay, doesn't matter. So, that's why w can also be a free variable. This is perfectly meaningful. It only contains logical symbols, primitive symbols, or previously defined symbols. Now finally, uniqueness. You might remember before we defined subtraction when we were doing arithmetic, first I proved that there was one and only one number that satisfied what that difference came out to. In other words, we proved that there is a unique additive identity is what we did. And then when we subtract y, that is using the unique additive identity. So there's always a uniqueness proof before you define a new operator. We need to show that applying that operator to 2 numbers always spits out one and only one number. It can't possibly spit out multiple numbers. I cannot take 1 minus 3 and potentially get more than one number. It has to give me one and only one number. So I don't know if you remember that far back to arithmetic, but before we ever introduce the definition of subtraction or division, we first have to do a uniqueness proof to show that these operations give us one and only one number. So anytime you introduce a new operation symbol, this is typically a theorem that comes before the definition to prove that this is in fact the case. Very common in most good math textbooks. It will either come right before or right after the definition to make sure the reader knows, and it's well defined, don't worry. And we also did that in arithmetic. Now, let's give an example where we couldn't do this. So let's go back to our definition of division. You might remember, what do we mean by x divided by y equals z? By definition, that was x is equal to y times z. Almost. This is almost what our definition was. We're cheating. What are we missing? Let's look at a concrete case of this. So if x is 15, what is 15 divided by 3 equal to? 5. And how can I prove that? The way I would prove that is I would check what is 5 times 3 equal to? Or 3 times 5. And I would come, knowing what I know about multiplication, I would check that and see that that is 15. And that is in fact the case. So this is in fact valid. That's the definition. What do I mean by x divided by y equals z? I mean x is equal to y times z. We used multiplication to define division when we did it.
But y can't be 0.
But y can't be 0. So this only works where y is not 0. Why did we have to put that restriction on y being 0? If we do not put that restriction on y being 0, then this is no longer a provable statement.
Because we violate the criterion of non-creativity.
It's one way that, well, I don't even know how to say that. Are you creating something?
Well,
Yes, you would be creating something. So yes, you can view it as violating that criterion, or you can view it as violating this rule. This would no longer be provable. So let's just play with this for a second and play with why dividing by 0 doesn't work. So imagine that I said some number divided by 0. Let's just pretend it had an answer for a second. Let's pretend you worked it out and it came out to a. What would that mean? By definition, that would mean that b is equal to 0 times a. That's the definition of b divided by 0 equals a. That means b is equal to 0 times a. That's its definition. Now you might remember in arithmetic we proved 0 times anything is 0. So that would mean that our b here had to be 0.
That seems like valid to me.
Okay, so then b has to be 0. So 0 divided by 0 is a. For which a? Notice that we didn't put any restriction on a here. It works if a is 0, it works if a is 1, it works if a is 2, it works if a is 3. And so 0 divided by 0 is 1, and 0 divided by 0 is 2, and 0 divided by 0 is 3, etc. And so 0 divided by 0 is now any number you want. So we see dividing by 0 doesn't work, except for maybe in the case where you do 0 divided by 0. You might think for a second, well, that kind of works. Shouldn't that be some number, a? Pick any number a you want, and it works. Can give you a quick pictorial intuition for also why that works from your algebra, if you're more comfortable with that. Pick some equation of a line. Just putting a pin in this. Pick some equation of a line like y is equal to 2x. What is that line? That is a line that goes through the origin and has a slope of 2. It goes over 1 up 2. Not a very good line, but over 1 up 2, over 1 up 2. Here's roughly what that line looks like, right? And in particular, everywhere on that line, just rewriting this equation, we get that y over x is equal to 2. Your y coordinate over your x coordinate is always 2. So if I come over here to the point 2, 4, here's the point 2, comma 4. My y coordinate divided by my x coordinate is 2. Pick any point you want on that line. The y over the x is 2. And I can pick some other line here. Let's just look at y equals x as a simple one. So that's a line with a slope of 1. Maybe I'll do purple so you can see it a little bit better. Here it is, roughly. There's our purple line. And on our purple line, everywhere, y over x is equal to 1, right? Now notice both those lines go through
Origin.
the origin. So what's the xy coordinate at the origin? 0, 0. So on this line at the origin, we get 0 over 0 is equal to 2. And on this line at the origin, we get 0 over 0 is equal to 1. And pick a line with any slope you want, and you can get 0 over 0 if it's going to be defined. We can make it come out any number we want by just picking the line with that as a slope. So another way that divided by 0 is just broken. If you might think the special case 0 divided by 0, we should be able to do something with that. The answer is no. If you try to make it something, you'll make it everything. And so it can't be unique here. And the author has a lot to say about dividing by zero, if you want to read more about it. He makes way too much fuss about it, but it's like 1/3 of the chapter is talking about dividing by zero.
There can only be one. Okay, I see.
There has to be a unique W satisfying S, whatever S is. Here's our formula S. So once you get an X and Y, there has to be a unique W. Or in other words, when you apply the operation to two numbers, it has to give you one and only one answer. It can't give you multiple answers.
Is that really the only scenario where you get multiple answers?
With division,
With division?
the only way you get multiple answers is when you divide by 2. When you divide by 0. Did I say divide by 2?
You did. That's all right.
I don't know where that came from. Okay. Any other questions about operators? Okay, so now constants. Kind of made a mess of what we have here. All right, so with constants, the constant C equals W. We can define to be some formula S. And it's well defined if and only if it satisfies these 3 properties. Number 1, W has to be the only free variable in S. Why can't C be a free variable in S? Because it's a constant, and a constant is not a variable. So the constant C equals W is defined to be whatever this formula S gives us. W is the only free variable in S. C can't be a free variable in S because C is a constant. Okay, second, S can only contain all the things we said before. Symbols of logic, primitive symbols, and symbols that have been previously defined. And then finally, there has to be a unique W such that S. In other words, when I define a constant to be a thing, it has to be just that one thing. I'm going to give you a special name, Bob, and it means anyone I'm talking to. Well, now it's not talking about one and only one person. So if it's going to be a constant, it needs to be talking about one and only one thing, one particular individual thing. That's what a constant is. 1 is a constant. What number is it? It's the number 1. X is a variable. When I say X is less than Y, I'm not telling you anything about any particular numbers. 1 is less than 2 is very different. That has 2 constants. So, give you examples defining a constant. Huh? Never mind. Give you an example defining a constant. We say 2 is equal to W if and only if W equals 1 plus 1. It's the long way. It's exactly how we define 2. It's kind of a long way for doing it, but a perfectly valid way for doing it. Now you'll notice that every time we do our definitions, we've been using these colons with a back and forth arrow, colon with a back and forth arrow, colon with a back and forth arrow. You can always use the logical equivalence operator when coming up with a definition. When you are defining an operation or a constant, you may also use equals. So rather than defining it this way, I could have done what I've already been doing all over the place. I could have said 2 by definition is equal to 1 plus 1. And you see how it's kind of just like bridging the W's there. And so, for your constants and for your operations, it's very common that there's a way to define them using equals rather than the logical equivalence operator. I personally don't like this definition for subtraction. It's not the one I use. The definition of subtraction I use is x minus y. I define that to equal x plus y's additive inverse. So first we would prove that y has a unique additive inverse, and that's what we mean by negative y. Now what do we mean by x minus y? We mean x plus y's negative inverse. Similarly, the way I personally like to define division is x divided by y. I like to define that to mean x times y's multiplicative inverse. So first prove y has a unique multiplicative inverse, and then that's the definition I would use using the equal signs. So I like using the equal signs more than using the logical equivalence when I define operators or constants. One isn't better than the other. It's just preferred or not preferred, depending on what you like.
More simplified, seems like.
I think it's more simplified, yeah. So, as examples, x minus y could have been defined that way. Example from geometry, what is pi? Pi is defined to be circumference over diameter. Don't have any of my geometry students here, but in geometry, before we do this, we prove that pick any circle you want, the circumference over the diameter is always the same. And so first we had to prove that circumference over diameter is identical for all circles, and then we could define that constant to be a constant. So in geometry, when you do geometry, you do this proof. You prove that there's that it is unique. That for any circle you pick, circumference over diameter is one and only one number. Whatever that number is, we call it pi. And then pi happens to be, when you do its numerical approximation, 3.14159, blah, 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 blah. But that's its definition, and that's a proof that you do before you define pi in geometry. Think we did the rest of those. Okay, so that's it for our theory of definitions. Pretty straightforward. Any questions on it? All right. Go ahead.
So, all numbers are essentially defined as constants.
Yeah, every number is a constant.
Okay, just wanted to make sure.
Good. All right. Let's jump now to next part. So now I am just going to give you an example of some different types of logic. So we are now done with logic proper. That's it. That's the end. That's logic. You now covered everything that there is to your typical first order logic course, or propositional first order predicate logic with identity course. So now, completely switching gears here to something new. Going to give you an example of an axiomatic system that uses modal logic and that uses second order predicates. Just to give you a flavor for what these other things are. So the one that we're going to use is Gödel's axiomatic system that he uses for his proof of the existence of God. We're going to use it because, well, it's pretty famous for one. Two, it's one that I already know pretty good, so easy on me. And three, it's a pretty simple system. There's not that much to it. There's like 5 axioms, 3 definitions, and 4 theorems. Something like that. So, going over Gödel's proof, it's called his ontological argument. Ontology is the study of being, so it's an argument from being for the existence of God is where that name comes from. More of a interest in philosophy. Here's the whole system, everything that we're going to be covering. So, we're going to have a total of, we're going to go over axiom 1, axiom 2, we'll prove a quick theorem, introduce a definition, then introduce the next axiom. When it's all said and done, there's a total of just 5 axioms, 4 definitions, or 4 theorems. Our last theorem will be our 4th theorem, and 3 definitions.
How would you define the definitions for axioms?
Just not introducing the axiom any sooner than you need it. Just to try and keep it as clean as possible.
Got it.
So this is, if you were to Google Gödel's argument for the existence of God, you would most likely find this spill out, which doesn't do much for you. It says, okay, go in this order, but it doesn't tell you how to prove anything, and if you want to teach it, you're going to have to go figure out how to do those proofs yourself. Probably. Speaking from experience. Okay, so here's what we'll go over. We'll try and break this down into some more bite-sized pieces. Before we do that, since we're going to be using modal logic, let's really quick talk about modal logic. Modal logic, we're just going to be introducing 2 more symbols. The 2 symbols that we're going to be introducing are that square. Can you guys see that okay? Don't need to turn off a bank. So we're going to be introducing that square symbol. Now the way that that is read is necessarily. This is the necessary operator, and then this diamond-looking thing is the possibility operator. Possibly versus necessarily. intuition for what this means. If something is necessarily the case, it means it could not have been otherwise. That's what they go for with necessarily. And possibly the case just means it could have been that way and it could have not been that way. And maybe it happens to be that way, maybe not.
Necessarily sounds a lot like implies or something. I don't know.
We'll give you some intuition for it. So first off, if X is a theorem, in whatever system you're talking about, remember, you use logic to construct systems. So now we're in some sort of system. If X is a theorem in your system, what does it mean for X to be a theorem in your system? It means it's a statement that is always true in your system. In the system of arithmetic, 2 plus 2 equals 4. That is a theorem in arithmetic. It's a statement that is always true in arithmetic. It's something that is entailed by the axioms. So if X is a theorem, it is necessarily the case that X. So if we're in arithmetic, I can say not only is 2 plus 2 equals 4, but I can say it's necessarily the case that 2 plus 2 equals 4. It could not have been otherwise is intuition for it. So statements that are guaranteed to always be true, things that you've shown are always true, are necessarily true. This is a way to read that. Rule 2, it's just a distribution thing. If it's necessarily the case that X entails Y, then X necessarily being the case entails Y is necessarily the case. If it's necessarily the case that my wearing shoes implies I'm wearing socks, then if I'm necessarily wearing shoes, I'm necessarily wearing socks. So, distribution 1. This one, if something is necessarily true, then it's true. So, necessarily true is somehow stronger than just being true. You're wearing shoes right now. It is not necessarily the case that you are wearing shoes. That's not something that we derive from the rules of how this universe functions. It's very possible that you could exist in a state not wearing shoes right now. That is not a necessary fact of this universe.
Is it taking into account time or space?
Just trying to establish intuition
Okay.
for what these things mean. Okay, duplicate necessary operators doesn't mean anything. If it's necessarily X, then you can say it's necessarily X. And you can go on your merry way repeating necessarily to your heart's content. Similarly, if it's probably the case, then it's necessarily probably the case. And adding that, I thought we were going to do probably. That one's also true. I wonder if that was a typo for a second, but it's not a typo. If something's possible, then it's necessarily possible. Next rule is what I was getting at. All the necessary operators you want lined up in a row is as good as just one necessary operator. And all the possibility operators you want lined up in a row is just as good as one probably operator. And then finally, alternating. So star here is a stand-in for square or diamond. I could have square, diamond, square, diamond, square, diamond. As long as it ends in square, that's all the same thing as just square. If it's necessarily, probably, necessarily the case that you have X, then it's necessarily the case that you have X. And whichever comes last dominates. And similarly for possibility. Doesn't matter what all the stars were before, as long as it ends in possibility, then it ends in possibility. And then finally, this is just to give you intuition. We could have defined that it is possibly the case in terms of the necessary operator. You don't need it as its own primitive symbol. You could have just introduced this as your primitive symbol and gone and defined this in terms of this. And what does it mean for something to be possible? It means that it is not necessarily the case that it couldn't happen. That's what it means for it's possible for it to happen. It is not necessarily the case that it couldn't happen. That means it's possible. And that's one way that you could define it, and I think that just helps connect your intuition between what these symbols are saying. One common thing that's pointed out between these symbols, one way to think about it, is people often think about this as functioning kind of like an existence quantifier, and this one kind of like a universal quantifier. This one's kind of saying there exists something where it's the case, and this one is saying it's always this way. And they have the same distribution rules. When I say that there exists X, such that some predicate about X, that is logically equivalent to, it is not the case that for all X, that you do not have P of X. If there exists a white swan, it is not the case that all swans are not white. Similar relationship there. And that's a common guiding intuition. Okay, so that was a quick blast through of modal logic and giving you some of these things. We're not going to use all of modal logic. I'm just trying to give you a flavor for it and how it works.
Does this basically take into account probability?
No. Probability is something that exists. You cannot confuse this possible operator and probability. Probability, a probability function, is something that exists inside of a sample space. It is its own mathematical construct, its own axiomatic system. And we do not need any of this for it. It only relies upon first order logic. Yes. And so that's one of these little axiomatic systems. If we were doing discrete math, it's one of the simple ones that you only play with for a bit. So don't confuse those two things. Okay, good, because that's coming. I thought there was one more thing I was going to say, but we'll say it as it comes up, I guess. Oh, here's the last thing I was going to say. There isn't the modal logic. So there's people who, I'm not sure where the cutoffs are. There's people who say, I only like these rules. Other people that say, no, I like the rules to here. Other people that say, no, I like the rules all the way down, and I think they're all great. And there's different versions of modal logic based off of how strict or loose you're going to be with the rules. I don't know what modal logic Gödel used. So I'm going to use all these rules because it's easier to have the rule than to not have the rule. I'm not sure what you have to prove this system. And we'll loosely make reference to these rules. I think for the most part, your intuition will be able to bridge the gap and we won't need to hard code look at the rule. But it's also nice to see the exact rule in action, I think. So with that, just trying to give you some intuition for what all these symbols are going to mean as you see them here before we jump into the system. So anytime you see X and Y, from here on out, these are going to represent objects. You, me, Bob, the table. Physical objects are what X and Y are going to be. They'll always be variables for things you can touch, poke. Assuming you can poke a god. Okay, next, I'm going to use phi and psi, Greek letters here. These are going to be variables representing properties. Now, these are predicates that take one term and they spit out true or false. Phi here is going to be like the is red. And when I pass x into phi, it's going to return true if x is a red object, and it's going to return false if x is not a red object. So phi and psi, these are both always and forever going to be one-term predicates, which is what we call properties. They're going to take objects and spit out true or false. So our domain of interpretation is everything in the universe is one way you can think about it. These are going to be any properties any object can have. Okay, now P here is going to be a second order predicate. Introducing it to you. It's very simple what it is. P is a positive property predicate. It takes as its input, not objects, but it takes as its input predicates that take objects. Predicates that take objects we call first order predicates. Predicates that take objects we call second order predicates. So P here is a positive property predicate. Is going to return true if you give up a positive property and false if you return a negative property. So if I throw the property of being courageous into P, it's going to return true. If I throw the property of being a coward into P, it's going to return false. So P is a positive property predicate, and it's a second order predicate. Your intuition will follow this pretty well, I think just fine, but thinking through carefully what exactly they are, I think is useful. So an example, you'll see phi will take in x's and y's. P will always be taken in phi's and psi's. Okay, and just a reminder, and so if I want to say phi is positive and psi is positive, that's how I would read it. It is not the case that phi is a positive property, is the way we would read that. The implies arrow, if x has property phi, then x has property psi. Is equivalent to x having property phi is equivalent to x having property psi, is how we would read that. The for all x has property phi, everything has that property. is the way that we'd read that. There exists something out there, there exists an x such that x has property phi. It is necessarily the case that there exists something with property phi, and then it is possible there exists something with property phi. Just reading some statements using all this terminology, and with that, I think we're ready to jump in and break it down. So now we're just going to go line by line through what I had listed at the beginning. We're going to go line by line through this thing and just make it make sense as we go, prove the theorems as we go. So I'm just going to be explaining exactly what it says or proving the theorem if it's a theorem. So starting with axiom 1. Here's what axiom 1 says. It says, notice that we have a whole implication here. So if this, then this. So starting with the if. If phi is a positive property, and it is necessarily the case that for all x, if x has property phi, it also has property psi, then psi must also be a positive property. I'm going to try and give you a couple intuitive ways to think about this. If phi is positive, and having phi means you also have property psi, then psi must also be a positive property. Positive properties can only entail positive properties. I cannot conclude from knowing your y's that you're a coward. If y's is a positive property, and coward is a negative property, I can't just by knowing your y's come to the conclusion you're a coward. That would be a positive property entailing a negative property. Say it in a couple different ways. If a property phi is positive, and it is necessarily the case that for every object x, x having property phi implies x also has property psi, then psi is also positive. Or say it again. If x must have property psi anytime it has property phi, and phi is positive, then psi must also be a positive property.
Follow.
Our first axiom here is saying that if I know you have one particular positive property, I cannot conclude from that that you have some negative property out there. If I can somehow conclude you have some other property, it must also be positive.
Well, why is it, if it's saying, it sounds so contradictory for you to say, you can't conclude, and then saying, well then you must also have,
Not you must have.
must also have, be
If
a
it is
positive property.
necessary, trying to think of two positive properties that happen to be related. I don't know. A positive property is working hard and having a good income. Let's pretend that one entails the other.
Okay.
So we're saying that if working hard is a positive property, and it is necessarily the case that every single person out there who works hard also has a good income, then having a good income must be a positive property. If one property is entailed by a positive property, it must be positive.
Kind of like saying, for something to be good, it has to produce good fruit type of concept.
Right. A positive thing, if it entails something, it must also be positive. A positive thing cannot entail something negative.
Gotcha. Otherwise it's not positive.
Well, we're not going to define what positive is.
Oh.
That's going to be one of our primitives, right? So let's start noting what are our primitives so far. Maybe we'll scribble these up here as we go. So far P is a primitive. Outside of that, every other symbol here is a symbol of logic. Remember that we're now in modal logic. Modal logic is built on top of all the logic we've done so far. So we can use everything we have so far, and now modal logic is just introducing that symbol, and we didn't use the other one there, and then also allowing us to go beyond just first order predicates. So our primitives can now be second order, third order, however many order predicates we want. In this system, we'll only go as high as second order predicates. First and second, that's it. Okay, what does axiom 2 say? Axiom 2 says that if not having phi is positive, if not being a coward is positive, then being a coward must not have been positive. If not having a property is positive, then that property must not have been positive. Not having phi is a positive property if and only if phi is not a positive property. Another way to think about this is this to give us that lacking a positive property is the same thing as having a negative property, and vice versa. lacking a positive property is the same thing as having a negative property, and vice versa. Now this also gives us something strange, and it gives us that every property is either positive or negative. There's no such thing as a neutral property in the system. Because if it's not the case that phi is positive, then not phi must be positive from this axiom. So that's what axiom 2 is giving us. Good so far? With that, we're ready to prove our first theorem here. Now, we'll kind of scribble it out here to the side and then go through that, I think, just to help you guys make the connection. So, theorem 1, we're trying to prove that if phi is a positive property, then it is possible that there exists something out there with that property phi. If phi is positive, then it's possible that there exists something with that positive property. That's what we're going to prove. So, we're proving an implication. How do we start an implication? Assume the antecedent. So we're going to assume, we'll start here by assuming P of phi. Assume whatever phi is, it's a positive property. Now we're trying to prove that this is the case. We're going to come at this by proof by contradiction, so I need to negate this thing. Now first I'm going to just rewrite this thing. Remember that the possible operator is not necessarily not. If it is possible to have x, that's the same thing as it is not necessarily the case that you do not have x. If it's possible to have x, it is not necessarily the case that you don't have x. That's what it means by it's possible to have x, right? So I'm going to just rewrite exactly what this is saying. Exactly what this is saying is not necessary, not there exists such that phi of x. Just flat out replacing that. You with me so far? Now we know how to distribute a not over an existential quantifier. What do?
All.
We switch it to a for all.
And then not the argument.
Right. So still just rewriting this says not necessary for all x not phi of x. So that is the same as that is the same as that. Now, remember, we're trying to prove that this is the case. So I'm trying to prove that this is the case, so I'm trying to prove that this is the case. And I'm going to do it by way of contradiction. I'm going to show that not this is the case, which will be that, is impossible. Therefore, this is the case, which means this, which means this. You with me? So, assume by way of contradiction that it is necessarily the case that nothing has property phi. So assume by way of contradiction that it is necessarily the case that for all x, it is not the case that phi has property x. This is the contradiction of that. Assume by way of contradiction that it is necessarily the case that nothing has property phi. Let me show how this leads to contradiction. And therefore, that will be true. With me? So I've seen the modal logic piece of it. So, then for all x, phi of x implies psi of x is vacuously true. Now this is what we're saying up here. Nothing has property phi. What has property phi? Nothing. So looking at axiom 1, we're going to be using axiom 1 here. I just rewrote down here for us to think about it. Notice that this implication shows up in axiom 1. Now this phi here that we're talking about, we already know that nothing has property phi. No x has property phi. So it is necessarily the case that for all x, phi of x, this is always going to be false. When we use this axiom, we're going to use it here in a second. But my point is this implication inside of here is going to always be true. Vacuously true. Because we're going to get false implies something. So then, for all x, phi of x implies psi of x is vacuously true. For any property psi I choose, I'm going to choose the property not phi. I'm going to let psi be not phi. So using axiom 1, rewriting this out, using axiom 1, I'm saying, from axiom 1, we know if positive applies to phi, and it is necessarily the case that for all x, phi of x implies my psi here that I'm choosing is not phi, some other property. Implies not phi of x. This whole thing together implies my psi is a positive property. If I can show a property is positive, and it's necessarily the case that for all x, phi of x implies some other property about x, then that other property had to also be positive. So just using axiom 1, plugging in psi for not phi. So then by substituting psi equal to not phi into axiom 1, we get that not phi is positive. Axiom 1 says that if phi is positive, and for all x, phi of x implies not phi of x, then not phi of x must also be positive. That's using axiom 1. You see it?
Okay.
So we just barely concluded, if you're able to give me this, I'm able to use that and the fact, so I have this information, and I also have the information that we started with, namely P of phi. So I know what? I know whatever phi is, it's a positive property. Here's what I know, and I also know this thing. Since I know this thing, then I know that this is always true. Phi of x implies not phi of x is always true, because phi of x is always false. I know this is the case for all x. And so, not only do I know it's the case, I know it's going to necessarily always be the case. And so I know that this piece here is true, and I know this piece here is true. True and true, since these are both true, that has to be true. And so combining that together, I know not phi is a positive property. So then by substituting psi equals not phi into axiom 1, we get that not phi is a positive property. Now from axiom 2, what does axiom 2 tell us? This tells us that phi, or not phi being a positive property, gives us that phi is not positive. But notice our starting assumption is that let phi be positive. Now we're getting not phi is positive. And so we're left with the contradiction, both phi is positive and not phi is positive. Contradiction. Therefore, the negation of this, which is this, which is that, which is that. Therefore, it is possible that there exists an x such that phi of x. That's a mouthful. It's tough using all these new symbols.
Yeah.
And following when we're talking about predicates. So, a lot of symbols, but hopefully it's clicking.
I guess sometimes I forget exactly what P and psi mean.
So we assume that this was true, and by getting the negation of this, we were able to show that the second thing is true. So this true and this true gives us that this is true.
These are just two arbitrary properties of a person.
What we showed is that if a property is positive, then it is possible that there exists something with that property. Because if it was impossible, it turns out that that property was both positive and negative.
Okay. I could argue that, but I'll
Well, we just went through the logic of it.
this whole thing's making a lot of assumptions that I don't necessarily agree with.
The only assumptions so far are the two axioms.
Yeah.
Those are our only assumptions.
Well, the whole fact that the assumption is a positive property is a challenge.
Positive is an undefined term. Don't impose any of your own intuition as to what these words mean. What do we mean? It could be that is foo. Some property is foo or it's not foo. And we're just dividing them into foos and not foos.
Well, but I think if you're trying to quantify it.
I'm just trying to give you intuition to help guide you through the system as we go.
Okay.
The same way that the first time we did group theory, let's think arithmetic.
All right.
But our only assumptions are two axioms. That's all we've assumed. Which is that axiom 1, if a positive is property, and it necessarily entails some other property, that property has to be positive. And axiom 2, which is every property, essentially says every property is either positive or not positive.
Wait, so you're using the term property.
So property is a technical term. What is a property? A property is a one-term first-order predicate. It's a predicate that takes an object and spits out true or false. Is red is a property.
Yeah, I understand.
So phi and psi here are always properties. Property is a technical term the same way variable is a technical term.
I'm just saying that we're somehow quantifying, are we somehow quantifying these properties into like a number system, essentially, where you have positive numbers and negative numbers, or is that not a good connection?
I want to think about it in terms of positive numbers and negative numbers. The intuition to guide you is being courageous is a positive property, and being a coward is a negative property. That's the intuition that will guide you best.
I wish I could use some intuition that I understand.
If you wanted to think about it, you could think about it. If you're trying to come up with some numeric thing, the positive here is kind of like acting like is even or not even.
Well, if you're defining some type of objective, and the closer you are to that objective, you could define it as a property.
Well, I don't know how to talk about closeness. You now want to talk about a metric, and we got to do a metric space. And this doesn't have all the structure of a metric space. It's a much simpler axiomatic system than that.
Yeah, I know. That's why the intuition is difficult for me.
So, intuition is the intuition, but all we're assuming so far are the two axioms. So the two axioms together entail this. No way around it. They entail it. With modal logic. You can reject modal logic, but if you accept modal logic and you accept the axioms, you have to accept theorem 1. There's just no way around it. All right, definition 1. And then axiom 3. Definition 1. We're going to define the godlike property. So defining a new property here, should have a colon there. The godlike property. What does it mean for an object to be godlike? It means for all properties out there, if that property is positive, then X has it. That's what it means for X to be godlike. It has every positive property. That's going to be the godlike property. Pretty straightforward definition. What does it mean to be godlike? For all phi, if phi is a positive property, you got it. Hard to think of a better name for having every positive property than that. Okay, so let's just read what I have. An object X is godlike if and only if, for every property phi, if phi is positive, then phi is a property of X. Or in other words, a being is godlike if and only if they possess every positive property. Axiom 3 is that being godlike is in fact positive. It is a positive property to possess every positive property. We're going to assume that's a positive property. So there's our third assumption. We're listing out the assumptions we're making. All right. Property being godlike is a positive property. Okay. Second theorem. It is possible that there exists something out there with the godlike property. That's what we're going to prove. It is possible for there to exist a thing possessing the godlike property. Or in other words, it's possible that God exists. Putting a standard interpretation on. All right, so let's go over this one. This one's pretty straightforward. If you remember Theorem 2, Theorem 1. Here's Theorem 1 that we proved before. Remind ourselves what Theorem 1 says. Theorem 1 says that if a property is positive, then it's possible that there exists something with that property.
So there's something that exists with all the positive properties.
For every positive property out there, it is possible that there exists something with the property. Not there is something with the property.
Right.
It's just possible for there to exist something with the property.
Yeah.
That's what we're saying.
Yeah,
So, from axiom 3 is the one that said being godlike is positive. Right? So axiom 3 gives us that being godlike is positive, or that the godlike property is a positive property. From Theorem 1, we know that if a property is positive, then it is possible that there exists something with that positive property. That's what Theorem 1 says. Just combining those two together, therefore it is possible that there exists something with the godlike property. Think of the 4 theorems, that's the easiest one. So there we go, that's Theorem 2. We're halfway through the theorems, just 2 more to prove. Any questions so far?
Makes sense.
Next one, definition 2. Is what it means to be an essential property of U. So phi is an essential property of X. What does that mean? Again, should have had my colon there, defining it. So, in order for phi to be an essential property of U, first off, phi has to be a property of U. If it's going to be one of your essential properties, it has to be one of your properties. So for phi to be an essential property of x, phi must be a property of x, and it must be the case that for every other property out there psi, if psi is a property of x, then it is necessarily the case that anything that has your essential property, phi, also has your property psi. This is the biggest definition to swallow. We'll say this a few different ways. Try to make the intuition quick. So, we call phi an essential property of x if and only if two conditions are met. One, object x has the property phi. If phi is going to be an essential property of x, object x must have property phi. And two, for every property psi, if object x has property psi, then it is necessary that for every y, if object y has property phi, then object y has property psi. Try saying this in simpler terms now. This is like trying to read it directly. So I do trying to read it directly, and then I try to simplify it down here to make it more intuitive. So try to make it more intuitive now. We call property phi an essential property of x when x has property phi, and two, if any other object y has property phi, it also has every property psi of x. So, let's say I have some essential property. We'll say the essential property of me is just the property of being Donnie. We'll try and keep it simple. I have the property of being Donnie. If you can find any other object out there that has that essential property of being me, then they must have all my other properties. That's what it means to be an essential property. If you have my essential properties, that means you have every property I have. So if phi is one of my essential properties,
Does that mean all of your properties are essential?
no. Because you and I both have the property of having two hands. That's not my essential property.
Unique properties? No, is it then?
Well, not necessarily unique properties. Let's say that we're the only human beings on Earth right now, and you get your leg chopped off. You have the property of having one leg, and that's unique to you. It's not your essential property, because if I chop off one of my legs, I don't magically have all the properties you have now. So your essential property means, or the essential property means, phi is an essential property of x, if phi has a property of x, and if anytime some other object y has the property, then they have every other property psi that you have. In other words, if something is one of my essential properties, if any other object has it, then they must have every property I have, if they have my essential property. Or anything that is essentially me has all my properties. That's what it means for it to be essentially me, to have my essential property. Overstressing it, or feel like the definition is making sense? Let's just read through it one more time now. All the nitty gritty. Phi is an essential property of x, means that phi is a property of x, and for all psi, for every other property, if psi is a property of x, then it is necessarily the case that for all y, if y has my essential property, then y has my other property psi. If it has your essential property phi, then it has every other property psi that you have.
Is it because psi?
Psi is just some other property you have. So if you have my essential property of being me, whatever my essential property is, then you also have the property of having two arms, of having chalk on your fingers, of being 5'9", of da 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 da. You have all my properties if you have my essential property.
Okay.
Okay, that's the hardest definition to deal with. Okay, axiom 4. Axiom 4 says that if a property is positive, it is necessarily the case that it's positive. In other words, if being courageous is positive, it's necessarily positive. There wasn't some possible universe where being courageous happened to be a negative property. If it's positive, it's necessarily positive. That's what axiom 4 says. Second to last axiom. Good so far? Read what I have here. If property phi is positive, then it is necessary that phi is positive. In other words, every positive property is necessarily positive. Okay. Theorem 3. The toughest slide. I wanted to break this out into two theorems, but debated against. I could have gone either way. We are going to prove that if X has a property of being godlike, then being godlike is an essential property of X. Now, I wrote exactly what it means for G to be an essential property of X right here, so that we don't have to go back and look at that big hairy definition. So, this is just plugging in G for phi when we have the definition here. So the definition of phi being an essential property of X is this. I'm just going to rewrite this exact same thing out, except for I'm going to replace it with G. What would it mean for G to be an essential property? So G is an essential property of X means that G is a property of X, and for all psi, if psi is a property of X, it's necessarily the case for all y, if y has property G, it also has property psi. So if it has one of X's essential properties, it has all of X's properties necessarily. Okay, now here's what we're proving. So, we're proving an implication. How do you start proving an implication? Assume the antecedent. So we're going to assume whatever X is, it's godlike. So assume X is godlike. And now let phi be any property that X has. What am I trying to show? Remember, I'm trying to show that G is an essential property of X. So I'm trying to show the stuff over here. I'm trying to show G is a property of X. Well, we already have that as given, so that's trivial. And now I need to show this second part. I need to show that for any property, sugar. I used phi here and psi here. I should have done, we're going to do phi. Doesn't matter, it's just a different variable, but I'm going to reference phis here as we plug into that definition. Okay, so G is an essential property of X. What are we trying to prove? I'm trying to show that G is a property of X. I'm trying to show that for any property phi you choose, where phi is some property of X, it is necessarily the case that for all y, if y is also godlike, it has that property. So I'm going to try and prove this chunk next. You with me? So let phi be any property X has. I now need to show, so I picked one that X has. I picked one that satisfies the antecedent here. I need to show that the conclusion now follows from this. So I have G of X. I'm now picking some property of X, and I need to show that that implies that it is necessarily the case that for all y, if y is godlike, it also has that property. So let phi be any property of X. Now I know that X is godlike, and I know that phi is a property of X. So what do I know about phi? What does it mean to be godlike? What's our definition of it?
Positive properties.
You have every positive property. I know phi is a property of X. So what do I know about phi? That it must be positive.
Yes.
Now, let's be careful because there's a trap you could fall into there. I know G has every positive property, but maybe it has some negative ones too. It just happens to have all the positive properties. How do I know that I didn't secretly grab a negative property?
It's not possible.
It's not possible because having a negative property is the same thing as lacking a positive property. That's what one of our axioms said. So we know that X has every positive property and only the positive properties. Because having a negative property is the same thing as lacking a positive property. So I am now guaranteed that phi, whatever it is a positive property. So observe that phi must be a positive property by definition of G, by definition of something being godlike. All right, now remember what I'm trying to show. So we've already got this piece. We assume this and show that that implies this. I'm trying to prove now this inner implication here. Okay. So to show this inner implication, I need to pick a y, that's godlike, and show that they also have phi, whatever it is. So let y be any object such that y is godlike. And observe that since phi is positive, remember, what does it mean for y to be godlike? They have every positive property. Since phi is positive, then y must have property phi, because it's a positive property. So then, so far, here's what we showed. We showed that phi being a positive property implies that for all y, if y is godlike, it must have that property. if phi is positive, then for all y, if y is godlike, it must have that positive property. We showed that this is always true. Now we almost got what we want here. Remember, the only piece of this I'm missing is this chunk right here. I need, is it necessarily the case that for all y, g of y implies phi of y. Notice how this implication is this piece, but without the necessary operator. Now, taking this we showed is always true. Going back to our first rule of modal logic, all the way back, if x is always true, if it's a theorem of our system, is something that's always true, then that implies it is necessarily the case that we have it. So since this is always true, I can then replace that with, it is necessarily the case that phi being positive implies, for all y, if being godlike applies to y, that implies phi applies to y. And then missing my ending bracket here. So since this is a theorem, just rewriting out like that with the necessary operator is valid. That was using our first one here. If x is a theorem, meaning it's always true in our system, it is necessarily the case that x. Now I'm going to use the second one, which tells me I can distribute necessary operators. If it's necessarily the case that x implies y, then the necessity of x implies the necessity of y. So distributing my necessary operator here, I get it necessarily being the case that phi is positive, implies that it is necessarily the case that for all y being godlike implies y is a property of phi. That was using that rule. So, I know this is always true, which gives me that this is always true, putting that in front of it, which gives me that this chunk is always true when we distribute the necessity operator. Now, axiom 4 tells me that if a property is positive, then it is necessarily positive. So I know already that phi is positive, and I know that since phi is positive, I know it is necessarily the case that phi is positive. That's using axiom 4. Using what we have here, it necessarily being the case that phi is positive, gives us that it's necessarily the case that for all y, g of y implies that. So by axiom 4, we get it is necessarily the case that we have this, therefore it is necessarily the case that we have this. And so, it is necessarily the case that for all y, if y is godlike, then y has property phi. And so, there we go. Observe then that 1, x has a property of being godlike, and 2, for any other object y that has property g, it also necessarily has every other property phi of x. So therefore, g is an essential property of x. G is an essential property of x. How do I know? Because anytime you find some other y out there that also has that property, it necessarily has every other property that x had.
So
that's the toughest part.
if there's positive properties, then there is a G.
No.
Okay.
Maybe we're in some system that has no positive properties. But then it would have no negative properties, because the negation of a negative property would give you a positive property.
Or, I mean, wait,
So,
you're saying, I don't know.
well, what I said was bad. I shouldn't have said it.
Okay.
But G is defined as having every positive property. That's just its definition.
Sure. Huh.
So one of our primitives is just P, and P just divides every property into positive or non-positive. And then we define G in terms of P, and G is having every positive property. And then, well, yeah. So we just readily proved that being godlike is an essential property. If you're godlike, then anything else that's godlike has every property that you have.
Okay.
Okay. Definition 3, and then our last axiom. So definition 3 is the necessary existence property. What does it mean that I necessarily exist? What it means for me to necessarily exist is that pick any one of my essential properties, and there exists something in the universe with that essential property. If every single one of my essential properties necessarily exists in something, then I necessarily exist. That's what it means by me necessarily existing. It means all my essential properties necessarily exist somewhere. That's what this is going to say. So what does it mean for our necessary existence operator? It means that for every property, if that property is an essential property of you, then it is necessarily the case that there exists something in the universe with that property. What does it mean that you necessarily exist? It means that for all your essential properties, there necessarily exists something out there with that property. And remember, if it has one of your essential properties, it has all of your essential properties. So this would give you that all of your properties exist in something somewhere. That's what it means for you to exist, or essentially exist. That definition makes sense? Read it a couple ways I have it here. Object X has necessary existence if and only if, for every property phi, if phi is an essential property of X, then it is necessarily the case that there exists an object Y such that Y has property phi. That's a direct way of reading that. Trying to give the more intuitive way of reading it. We say X has necessary existence if and only if there necessarily exists something with each of X's essential properties. If there necessarily exists something with each of my essential properties, I essentially exist, or I necessarily exist. Not sure if I said that weird. Let me say it one more time. What does it mean that I necessarily exist? It means that for each of my essential properties, there necessarily exists something with that property. Couldn't have been otherwise. And then finally, our last axiom is necessary existence is positive. We're assuming it's positive to necessarily exist. And there's our last assumption. There's our last definition, putting it all together in the famous Theorem 4. Therefore, it is necessarily the case that there exists something with the godlike property. Or the way it's commonly said, God necessarily exists. So, from Theorem 2, I have it written right here. What does Theorem 2 say? It says it's possible that there exists something with the godlike property. From Theorem 2, we know that it's possible that there exists an X such that being godlike applies to X. Good so far? Mm-hmm. From Axiom 5, we get that necessary existence must then apply to X. Because necessary existence is positive. Being godlike is having every positive property. So from Axiom 5, we get necessary existence applies to X. And by Theorem 3, right here, we know that G is an essential property of X. So since necessary existence applies to X, and since G is an essential property of X, then by definition 3, we are given that there necessarily must exist some Y such that G of Y. So necessary existence applies to X means that for all its properties, if it's an essential property, there exists something with that essential property. Our X here has the G property. So let's scribble out all the logic to the side as we go, messing with our expression. I think it will come together. So first off, starting with Theorem 2. I know that it is possible that there exists an X with G of X. That's what I know from Theorem 2. Now, I know that if G of X, if X is godlike, then that's an essential property. So then, I know that it is possible that there exists something such that, some X such that G is an essential property of X. Right? Similarly, I know since necessary existence is positive, and being godlike is having all the positive properties, I also know that it is possible that there exists an X such that E of X, necessary existence to X. Now, what does necessary existence mean? It means for all your essential properties, there necessarily exists something with that property. That's what this one means. So G is an essential property of X, and X has a necessary existence applying to it. So, combining that with definition 3, I'm able to get that it is possible that this piece, maybe I should take this one at a time. It is possible that there exists an X such that, substituting in this definition right here, I'm just going to plug this in for E of X, so I'm just going to rewrite that out. Such that for all phi, the one that we care about is the godlike one, so we don't care about all of its properties. We're just going to plug in the godlike one, using universal specification on that. So, G being an essential property of X implies that there necessarily exists a Y such that G of Y. Good so far? So we've got the antecedent here, and so we can now go to the conclusion. And so we can go to, it is possibly the case that there necessarily exists a Y such that G of Y. It is possible that there necessarily exists a Y such that it has that property.
Necessarily cancels out possible.
No, it doesn't cancel it out, but going back to Rule 7 here, all the ones that come before don't really matter. It's just your last one. It's just your one closest to the expression that matters. And so this is just the same thing as is necessarily the case that there exists a Y such that G of Y. So, since necessary existence applies to X, and since G is an essential property of X, by definition 3, we are given that there necessarily must exist some Y such that G of Y exists out there. So, therefore, it is necessarily the case that God exists. And that's the end of the proof.
Being something with all the positive qualities.
That is exactly the definition of a God in this system.
Gotcha.
Something that possesses every positive property. So, that's what we just barely went through, is all of these, explaining it all as we go. It's a nice little standalone system. I said it was a simple system. Don't mean to be rude by thinking it's easy to follow. When I said simple system, I meant only a few axioms, definitions, and theorems. It is not a trivial system in terms of ease to follow.
Yeah.
It's actually quite difficult and hopefully stretches you a bit to follow it.
Yeah,
So I think it's a good example of giving you a taste for modal logic, for second order predicates, and then just because this is pretty famous.
kind of using it in a real world examples, kind of saying.
Well, I don't know if you're going to use it in a real world example, but it's just exposing you to different axiomatic systems and
Yeah, no, it's cool.
what's out there. Yeah, it's a fun one. All right, any other questions? If it makes you feel better. My wife noticed on an episode of Big Bang Theory, and then Sheldon, he's trying to come up with a really hard lecture to confuse Wolowitz. And one of the things he has written on one of his whiteboards, someone wrote this. And one of his lines is, I'm not even sure what it means. So, if you understand that, you're smarter than Sheldon Cooper. Look at that.
No, I didn't.
Or at least I understand an argument that Keith Ramsey doesn't. It's a tough one, but it's fun.
Oh, yeah. I like having seeing some examples of it being used to explore possibilities.
Okay, we will end it there this week, and I have no clue what we're going to do next week.
Hopefully,
We'll figure that out.
vector spaces.
Vector spaces, I debated it.